All right, so mgh works plus the constant for the potential energy if we assume that little g, the acceleration due to gravity, is relatively constant. And assuming that we know what the value is. But if we are dealing with, say, outer space, we can't make that assumption. So if the force is the generalized gravitational force, G m1 m2 over r squared, the potential energy formula, as I wrote up on the board, is negative big G mass 1 mass 2 over r. There's no vector afterwards because energy is a scalar. Oh. Lesson. So I want to look at the situation of I've got a planet and I'm launching something from the surface of the planet and I never want it to return. Planet X. I'm launching something from the surface here, so the problem basically takes place is how fast does this thing need to be going so it never returns? We are making the assumption that it's not going to hit anything. So we're not worrying about air resistance, or we're not worrying about it's going to hit a satellite or a planet or anything like that. We're just launching it at some initial speed so that it never returns. I cannot use mgh because little g is getting smaller and smaller the farther out we go. Once it is launched, so let's take a look at this object when it is here. What are all the forces acting on it? Wait. I would nitpick that. I think the spirit of what you're saying is correct, but I would not call it weight.
Right.
Work on the wording. Again, the spirit of what you're saying is correct.
Gravitational force.
There we go. Gravity, huge topic, of which we'll get at a tiny piece of it. All right, it's a gravitational force. The reason I wouldn't call it weight is that this thing is only near the planet at the very beginning and then not after that. So little g is changing throughout the entire trip. Right? You could get away with weight, but it gets much more complicated if we're going to go that route. All right, so we have this gravitational force acting back this way. Likewise, there's a force pulling on the planet. Any other forces acting on the object?
No.
Okay. I saw a head shake also, but yes, that was correct as well. Some students will say, what about what launched it? I don't care what launched it. All we need to do is figure out how fast it needs to go after it's been launched. So the problem starts as soon as it's hit that, whatever VI is, so it never returns. Gravitational force, conservative or non-conservative?
Conservative.
Therefore, what can you tell me about energy? I suspect some of you are thinking, surely it can't be this because the answer is too obvious. It is.
It's the same energy. Same
Yeah.
potential energy.
Ooh. Be careful.
Work energy is equal to potential energy.
Same energy as no.
You're dancing around it. You see the ballpark. Then you're walking to the entrance. If only conservative forces are doing any work, why is it called a conservative force?
It's not wasting any energy, so it's using the same amount.
Okay, so I was hoping for just this quick answer of energy is conserved. That's what I was going for. But yeah, same amount of energy is at the beginning and the end. I have a conservative force, it is the only thing doing work, and just as a side note, is that force due to gravity doing positive work or negative work?
Negative.
Okay, I heard negative here, and you said?
If it's launched away from the Earth, then it's negative.
Yeah, because the force due to gravity is that way, and the displacement is that way. They're in opposite directions. Also, it's the only force involved, therefore the total work and the conservative work are the same thing. Total work is equal to change in kinetic energy. If it is slowing down, the kinetic energy is getting smaller, and the only way that kinetic energy can get smaller is if negative work is being done. All right, so we have the energy here is equal to the energy when it's has decided never coming back. I have two types, kinetic plus potential. This time it's gravitational potential, generalized gravitational potential, and is equal to K final plus U G final. I'm about to ask that question. Please make sure you have the answer in your head, ready to go. Chorus of angels. What's the formula for kinetic energy?
1/2 mv squared.
Doing it in rounds.
Yeah, let's go.
So 1/2 mv squared, initial. My potential energy, what's the formula for potential energy?
1/2.
Which one?
Thank you. The one associated with the generalized gravitational force, well, that's presented right there. So minus or plus negative, however you want to work that. G, mass of the satellite, mass of, this is mass of satellite, mass of planet X over R initial.
Squared.
No,
Oh, no, wait, that's.
energy.
Right.
Yeah, I'm so used to doing R squared on the bottom there that at some point I will write that by accident. Especially if you keep encouraging me to do that. No, it is just R, plus some constant. And then 1/2 M satellite, V final squared, plus negative G mass of satellite, mass of X over R final. Not squared, plus the constant. All right, so right off the bat, the constant goes away. At some point, I'm just gonna stop writing the constant, because we all know it's there. All right, so I have 4 terms there. Any of them equal to 0. You just get those right out of the way. The scenario is this has been sent from the surface of planet X, never to return. Let's take it piece by piece. All right, we're trying to find VI here. Is there anything in my equation, is there anything I can get rid of?
Mass.
Of,
Satellite.
yes. Mass of satellite is a factor in every term. So mass of satellite goes, mass of satellite goes, mass of satellite goes, mass of satellite goes. All right. We've already gotten rid of the constant. We're trying to solve for VI. Initial R, what is R? What is the initial distance?
1.
Are there any units with that?
1 year.
1 meter.
I would say 1 meter, probably not. 1 year, we're not quite at the point where we can connect time and distance.
G? Wait, do we know G?
Right, the distance.
Wait,
Okay, it launches from the surface of the planet.
that's.
What would be the distance? If I'm standing on the dirt outside, what is the distance?
0?
So if it's
That's
0,
undefined.
let's think about this. If it's 0, we have a 0 in the denominator,
That's undefined, so I think.
which would make this infinitely large. And I feel very confident that my weight is not infinitely large when I'm standing on the planet.
1.
If you're gonna say 1, I need some units with that. One what? In general, what is this R anyway? Besides distance. Distance between what?
The center?
Center to center distance. Technically center of mass to center of mass. So what would be the initial distance here?
0.
You're saying
Wait,
if
oh.
I launch it from the surface, it's at the center of mass?
Oh no.
I'm not looking for a number here, I'm looking for in general.
Radian? Is it like 1 radian?
What radian? That's an angle.
Something like that.
1 radius.
Yes. The center to center distance. The center of the planet is here, the center of the object is there. That's the distance. It's just the radius of the planet. So this is the radius of x. So we've now taken that equation. We have changed it slightly. So I have 1/2 times my initial speed squared, again, that's what we're trying to find, minus big G, mass of planet X over Rx equals 1/2 V final squared minus big G, mass of X over R final. So we take care of the left-hand side, the right-hand side we need to do something with. Let's deal with the final potential energy term. What do you know about R, the distance? Yes, we've launched this thing, what do you know about that distance?
Infinite.
So what happens to the fraction when the denominator goes to infinity?
0.
So that is 0 because RF is going to infinity. This thing's never returning, it's gonna just keep going. What else do you know about the object once it's been launched?
Slows down.
Yes. What's the slowest it can get? Or close enough.
0.
So it's going to keep slowing down constantly, but VF is never going to hit 0. If it actually does stop, it's going to come back. But VF is going to be close enough to 0. I mean, if it's going 0.01 meters per second, we square it, it becomes even tinier. This is approximately 0. And it's approximately 0 because VF is approximately 0. Because it's slowing down the entire time. It keeps slowing down. So we are now left with 1/2 V initial squared minus big G mx over Rx equals 0. So my initial speed in order to do this is going to be the square root of 2G mx over Rx. So now we can calculate that for the Earth. So that becomes the square root of 2 times 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th divided by 3.68 times 10 to the 6th. That's not right. Sorry, no, that number's wrong. No, that's the 5.98. Some of the numbers are getting all thrown together. That's 5.98. This is 6.38. 6.38 times 10 to the 6th. If someone would be kind enough,
Was that the 5.98 to times 10 to the 24th?
this is 5.98 times 10 to the 24th. That's the mass of the Earth.
And that's negative 11, the next one.
That's a negative 11. That's from the gravitational constant.
Like in space or something, or like, what does that mean?
It's the gravitational constant, potentially in the entire universe, but at least any experiment that we have done. It in essence, gets the units to work out.
And that's the radius of the Earth?
Yes, in meters. Giovanni, seems like everyone's counting on you.
Uh, 11,181.9.
11,181.9.
Thank you, this is so quick.
Is that what you said? Yep. What are the units?
Meters per second.
Yes. And I know it's 11,000 something, so I'm trusting the rest of it's right. All right, so the escape speed for Earth, if I can launch something and it doesn't hit anything, which is the tricky part, if I launch something at 11,181.9 meters per second, it will leave Earth and never return. And we do have things that do hit that speed and escape and never return. They are tiny. We lose a little bit of gas into outer space. Obviously, not a significant amount because we're still here. All right, so we now know what the escape speed is. We've manipulated this. Let's just take this one step further. Again, this all stems from conservation of energy. Suppose there's a maximum speed. So let's start out with the assumption that there is a maximum speed. To represent that maximum speed, I'm going to use the letter C from the Latin for celerity. So I'm going to stick this into my equation over there. So I end up with c squared equals big G mass of whatever that central object is over the radius of that object. Oh, and I lost my 2. I'm going to manipulate it slightly. I'm going to solve for the radius this time. So r sub x equals 2gmx over c squared. So what I want to do, assuming that that's the maximum speed, I can never exceed that number. This would be the formula for what's known as the Schwarzschild radius. Or probably better pronounced Schwarzschild. Schwarzschild was a physicist, German physicist, got caught in a mustard gas attack in World War I. And I don't know who launched the missile that got him. While he was recuperating in the hospital, he basically was working on some of Einstein's general relativity. The math for Einstein's general relativity had just been published a couple of years earlier. He was playing around with it and came up with this value here. Now, we did not use general relativity at all. It comes out to the same answer either way, the same equation.
Wait, so C is supposed to be equal to,
The maximum speed that an object can go.
what is this, well, is that the initial velocity?
No,
Or the,
no, it's that if my radius is less than whatever this value is here, then it is possible for something to escape. Light would escape if nothing else. This is, so, well, jumping to that, this is the speed of light, which is a barrier. Anything traveling slower than the speed of light cannot get to the speed of light. So it is a maximum speed for any object any physical object. So if we took our sun, 6.67 times 10 to the negative 11, that's Newton meters squared per kilogram squared, times the mass of our sun, which is 1.99 times 10 to the 30th kilograms, divided by the speed of light, which is about 3 times 10 to the 8th meters per second squared. If someone would be kind enough to do that calculation, then we'll talk about what it means. And hopefully answer Stone's question.
and so you did it